Thank you. Let me start by thanking the organizers for putting together this meeting. It is a great honor for me to be here today. Good. Thank you all for coming as well. Okay. I'm going to tell you a bit about a couple of papers from the last 12 months that I wrote with my great collaborators, Mark Halaberdian, Zvi Bern, Radu Roivan, and Dimitris Kosmopoulos, who is sitting over there, and Trevor Shebner and Fei Teng. They are in the audience. And this is also based on some formalism that we developed with Xiaoshen and Mao, who are also in the audience, and Justin Vines, who is no longer in the picture. So a disclaimer, this is a partial view. I say nothing about some amplitude adjacent methods like WQFT or PMEFT, Icona, which have many similar and overlapping results and many marvelous results. Also, it's not written here, but I don't give a lot of credit in the talk. There are many contributors to all of this program of spin in binary dynamics. Many of you are sitting in the audience. You will not see your name. Please don't be offended, or all of you can be equally offended. That's fine. Okay, here's an outline, an ambitious outline. I'm going to give you a very briefest introduction to amplitudes and binaries. Then I will tell you something about getting the dynamics of spinning binaries from amplitudes. And then something about going beyond spin and the significance of some extra Wilson coefficients for what we call generic compact objects. This is what we call the K degrees of freedom. For some of you that have read some papers, I will give two examples of systems that are described like that, and I will conclude. Okay. You all have seen talks like this. We need to carry some slide with a picture about the detection of gravitational waves. And then, of course, in the last few years, there have been detected through gravitational waves mergers, not only of black holes, but also of other objects, including neutron stars. Now, a need from having gravitational wave detectors is analytical methods to actually describe the dynamics to enable the detection and to exploit all of the data that is being taken by the observatories. And so we as a community, we got an invite from Thibaut Damour, who is one of the important figures in the computation for analytical dynamics for binaries. We got an invitation to use our novel techniques to compute. That was in particular a two-loop scattering amplitude of scalar masses, so that we got the Tirpitz-Minkowskian correction to the dynamics. This invitation, this challenge was issued in 2017. Then in 2019, the group led by Zvi Bern in California, they actually got this 3PM dynamics using all of the tricks in the toolbox. Using unitarity, spinor helicity, double copy, they got the important piece of the two-loop amplitudes, and they turn it into a Hamiltonian that will govern the interaction of two black holes at that order of precision. Okay, so what is the objective here? Go compute scattering amplitude and turn that into the description of a binary of black holes. That is the source of gravitational waves that we can measure. What kind of amplitudes? In principle, a 4-matter scattering amplitude can be 3-level. It can have loops. This will be a talk about one loop. The state of the art is now at all the way to 4 loops, partial results. Okay, how do we turn amplitudes into binary dynamics? There are many ways. What was done at first was use an EFT to generate a Hamiltonian. That is That was done because Hamiltonian is a language that the classical people spoke, so it was good to compare with them. But Hamiltonian is a very off-shell thing, so it's better to think on-shell. And then you can go directly from amplitudes to observables, for example, using the method developed by Kossauer, maybe, and O'Connell. Or we can use our amplitude as a generating functional through what we call iconal or these amplitude action relations. Okay. This is a talk about spin. Why are we interested in spin? First of all, sorry. Since now we have since now the orbital angular momentum is not conserved and it can be exchanged with spin, then the dynamics are not confined to a plane, and you can have much richer dynamics in the system. We know now that the astronomical black holes that produce the gravitational waves, they actually carry spin. So it is of astrophysical relevance. And perhaps more interesting in this room, because it has some very nice connections to scattering amplitudes. What do I mean by that? Even from the old days of 2008, Holstein and Ross went to compute some potential, correction to the potential and spin effects using something like, well, using scattering amplitudes. They were using Feynman diagrams like that. And what theory do they use? It's simply some massive spinning field that is minimally coupled to gravity. You can go higher order in spin. Barumbadia did that. He got all the way to spin to the fourth by considering a spin 2 fields. For things more related to these modern methods, let's talk about two papers from 2017. In one of them, Nima and Yutin and Suixin Huang, they describe what they call minimal coupling amplitudes. For all masses, all spins, and that is the simplest amplitude, is the minimally coupled amplitude. Also in 2017, with only a couple days difference, in a completely unrelated thing, Justin Bynes computed the stress energy tensor for a linearized Kerr black hole. A little later, it was understood both by the group of Guevara, Ochirva, and Bynes, and this with a couple locals, Young-Wook and Sang-Min Lee, that these two objects are actually equivalent. So this scattering amplitude, the minimally coupled scattering amplitude, is what you need to describe the scattering dynamics of a linearized Kerr black hole. Okay. So suppose you need a field theory that is going to describe not only black holes, but any compact object. And we would like to go ideally beyond only the linearized level. So how do we build a field theory like that? So we took a page from the a world line theory that has spin-induced multiples that was developed by Levy and Steinhoff. It was systematized by Levy and Steinhoff, building on the kind of formalism that Rothstein and Porter were already doing. And you could see you will have the whole tower of multiples, and they will be linear in curvature. So what we did was, okay, to describe spin effects, we are going to need to carry fields that are spinning. And if we want many orders in the multiple expansion, we need high spin. So we consider fields that are symmetric and traceless, arbitrary integer spin, and we minimally couple that to gravity. We have the covariant derivative there, and that is given in terms of the spin connection and the Lorentz generator. Now, in the classical limits, this Lorentz generator will turn into the spin tensor. And that is how our amplitudes will have the, I have to hurry, will have the spin in them. Going back to that Lagrangian that I showed you, that is for the non-minimal coupling, and we have all of these spin-induced multiples. We got that, and we took the covariant version of that. So this is all the non-minimal couplings of our spinning fields to gravity. Okay, and it has that spin operator looking thing that is given in terms of our Lorentz generator. Good. Once we had a Lagrangian to describe our spinning fields, we want to work, and we are after that one loop amplitudes. We compute the Compton amplitude using Feynman diagrams. It's not bad, it's only 4 diagrams. And then we use unitarity to turn this into a one loop amplitude. On the other side, since we want to obtain the dynamics of it, we have an effective field theory that is the generalization of the one developed by Chung, Rothstein, and Solon, in which the Wilson coefficients are these contact interactions, which is pretty much the potential of the field. And so one can compute the scattering amplitude in that effective theory, and by matching, we determine that Hamiltonian, which then one can turn into the observables that we're interested in. In this case, the linear and the angular impulse. Using this picture, we got results up to spin squared. And importantly, we did a lot of checks of this by matching to the literature. For example, to Hamiltonians from GR, both in next to leading order in post-Newtonian in the overlapping parts and in the test body limits. And we also obtained, we compared to aligned spin angles that were available in the literature. Now, I told you that this Hamiltonian, since it's going on shell to then go to observables, is kind of inefficient. Instead of doing that, we realized that you can actually go from the amplitude to an object which is the iconal phase. This is pretty much just a Fourier transform. And then from the iconal phase, you can operate with Dirac-like brackets, with Poisson brackets, sorry, to obtain the observables. Now, this formula was reverse engineered. We already knew the answer. We found that this actually reproduces it. We have kept doing that. It still works. It even worked with what I'm going to tell next. But there have been a couple of, well, a few papers recently where they have established a formalism in terms of Dirac brackets, which take into account all of the constraints from for the spin. I think Ricardo and Jungkook will be talking about something related to that. So don't miss those. Okay, just to summarize what I was telling you, we have a field theory from which we can get scattering amplitudes. And then from those amplitudes, you go to observables. It can either go through a Hamiltonian using an EFT to match the Hamiltonian, and then equations of motion will bring you to observables. Or we can use a differential operator on the iconal phase to get the same observables. Okay, and that works perfectly like we did up to spin squared. We were reproducing everything in the literature. What happens if you want to go higher to spin squared? In the spirit of effective field theory, what we are doing is an effective description of the multiples. You have to include every possible operator that will contribute to your answer. And so beyond those operators that I was considering, that are the covariantization of the Levy-Steinhoff word line, then we will also need to consider some tower of operators that also will contribute classically at the same orders. So then we have more EFT operator, more Wilson coefficients. And we can compute an amplitude from that. We go we compute the scattering amplitude, and then you get a scattering amplitude which has a lot of Wilson coefficients. What do you do with those? Well, you have to fix them somehow, and you can fix them through matching. We can do that and obtain the answer for the Kerr black hole. Now, our amplitude exactly, well, it has all of the freedom that it requires to be matched, and we can compute observables from that and see that they reproduce the literature. Good. But that's kind of, I don't know, not so pleasing. We wanted to obtain a Kerr black hole, or we wanted to obtain information from within. By looking at the coefficients for the Kerr black hole for some of the operators that you can have in the classical spin description, we realize that those kind of operators satisfy what was called a spin shift symmetry, which is if you take spin and you shift it by this q vector, classically, the amplitude is unchanged. Very pragmatically, that means that you cannot carry q dot a in that effective description once you have put it in some kind of basis. And we saw that the spin shift symmetry actually reproduces what the Kerr black hole is up to spin to the fourth. Why do I say that? Because this matches the results from black hole perturbation theory, the solutions to the Tucholsky equation. From spin to the fifth, apparently that's no longer the case, but also the problem becomes much more subtle because you have to consider absorption. But up to spin to the fourth, this seems to work nicely. And apparently at lower spins, but high orders in G, you still have some notion of that spin shift symmetry. And Mao will tell us about that next. So, okay. Up to spin squared, it was a very nice situation because there were a lot of results from GR. So everything we were producing, we had a lot to check. From spin cube, there are no longer a lot of results. So the checks are way more scarce. But up to order G squared and spin to the fourth black hole, we got consistent results with everything else that was available. And up to G squared cube for compact objects, like having still arbitrary Wilson coefficients, we were able to reproduce whatever else was around. Okay, but this is only after I have fixed my extra Wilson coefficients. The conventional way to describe the objects is that you have, like in the Levy-Steinhoff, one Wilson coefficient free for every order in the multiple expansion. And we have more than that with the H Wilson coefficients. So what do we make of them? Okay, we get to the beyond spin part. Computing amplitudes in gravity is more difficult, at least if you are doing Feynman diagrams, much more difficult than doing that in EM. So we resorted to look at the problem. So the puzzle is, why do we have more Wilson coefficients than the classical description? We did that in that paper. If someone has come across that, this is almost 100 pages, but I will try to give you exactly 5 points for that. We investigated our QFT, a word line for EM, and a description with a Hamiltonian. Now, what are the conclusions here? In the classical setting, your spin tensor will carry 6 degrees of freedom, but your minimal description, just in terms of spin, it only carried 3 degrees of freedom. In order to reduce these extra degrees of freedom, you impose that condition, which is called the spin supplementary condition. Okay. Imposing that spin supplementary condition in the word line is equivalent to carrying a single quantum spin in the field theory. We call that object that is described with only one Wilson coefficient per order in multiple expansion a conventional compact object. if you don't impose that SSC in the world line, that is equivalent to having a field theory which allows transition between quantum spins. And that is one of the characteristics of the theory that we were considering, the Lagrange that I showed you. So then this description in both sides will have additional operators and Wilson coefficients. We call that a generic compact object. Okay, we can obtain the results for black hole or for the conventional compact objects by taking our generic description with extra Wilson coefficients, extra degrees of freedom, and setting the Wilson coefficients to some value. In that sense, it's more general. You can always get the constraint case. For this generic compact object, the dynamics includes extra degrees of freedom, which we call the K vector. It will be clear why. And for the conventional compact objects, the magnitude of the spin vector is always conserved, but that is no longer the case for our generic compact objects. Okay, here is our field theory description for the generic compact object. It will have not only the C2 that is the same you would get in the conventional way, but also two more Wilson coefficients, and they accompany this this operator that you can see that on shell is proportional to that product, S mu nu times P nu, which is the one in the spin supplementary condition. So if you enforce the spin supplementary condition, it would be equivalent to turning that off. Now, going back to the spin tensor description, this you can express in terms of that spin vector and those degrees of freedom that are like a boost and that we refer to as the K vector. These are simply extra degrees of freedom that are obtained via that product, S mu nu times P nu. And that describes the dynamics of a more generic object than your simple one that is described only with the vector. We can do the same in a world line formalism. Originally, you would impose the SSC with a Lagrange multiplier. Just drop it. Then to encode the non-linear couplings, we put that into this function, one. Okay, into this function, that is the dynamical mass function, and that will carry the extra Wilson coefficients. This world line produces results that depend on this K, and we can always set D2 or E2 to 0 to obtain the dynamics of the conventional compact objects. I have to run because I have no more time, but once that I have that world line, I can use the equations of motion, the Mathison-Papapetrou-Dixon, to obtain observables or to obtain a Compton amplitude and reproduce exactly the same that I got in my field theory. Okay, this is a Compton amplitude. Importantly, very, very importantly, there is no linear in K contribution to the gravity. That is one condition that is necessary in gravity. There is no mass dipole there. Okay, I can go to a Hamiltonian that contains K degrees of freedom, or I can use an iconal that contains K degrees of freedom. If I compute observables, I observe that the magnitude of my spin vector is not conserved. Instead, I can recover the conservation by setting my Wilson coefficients to some value. I was going to give you two examples for this. One of them is scattering a scalar with respect to a bound system with Newtonian dynamics. I don't have time to do it, but you can ask me offline. And a second one is a black hole in exotic theory of supergravity. Yes, that is known as the Rashid-Larsen black hole. So I got to my conclusions, but then I finish. Just leave them there.